Well, the thing is, this one and this one we can eliminate in favor of lower order derivatives. How can we do that? You see, we have this, and we also have whoa, exciting. Sorry about that. Go away. Shush. These smartphones are dumb. Anyway, so if A2 is non-zero, we can solve for Y2 prime prime, right? What's this look like? YP prime prime. We got V1 prime, Y1 prime. What's this? This is plus V1 times what? Oh, I'm an idiot. That's not what I want to do. I'm making it very complicated. I'm making it very complicated, guys. I don't need to do that at all. I'm sorry. It's finally just penetrated my thick skull what the next step is. That's a stupid step. We could do that. Things would cancel out. It would be fine, but there's an easier way. And it turns out the easier way is just to plug what we have back in to our desired outcome. So in particular, we have AYP prime prime plus BYP prime plus CYP equals 2G. So we're just going to plug in what we've learned YP prime prime is, right? So that's going to be A times V1 prime Y1 prime plus V1 Y1 prime prime plus V2 prime Y2 prime plus V2 Y2 prime prime. That's my YP prime prime. And then plus BYP prime. YP prime was V1 Y1 prime plus V2 Y2 prime. And then my CYP, which was C V1 Y1 plus V2 Y2. All of that's equal to G. Now the beautiful thing that happens here that I was about to just mangle is something, there's something very nice that happens here. We've got an A and, excuse me, a factor out of it. You got V1 terms. V1 times A1 prime prime plus BY1 prime plus CY1. And you got a V2 times AY2 prime prime plus BY2 prime plus CY2. And then the other terms. The other terms remaining are a V1, V1 prime, Y1 prime, plus V2 prime, Y2 prime, and all of that's equal to G. Now let's do some counting. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I haven't missed anything. So what's the deal with the red terms? By assumption, Y1 and Y2 are forming the fundamental solution set. All right, those are solutions to the corresponding homogeneous equation. By assumption, the terms in red are 0 because we're adding those particular linear combinations of the first and second derivatives of Y1 or Y2. These are by construction 0, which is the beautiful thing I was about to butcher. And so, all right, what do we got then? We've got Y1 prime, V1 prime plus Y2 prime, V2 prime is equal to G over A. I'm going to put a box around that because the two boxed equations are really the heart of the matter. We just need to solve both of those boxed equations. What are my unknowns? I mean, I'm trying to find V1 and V2, right? But certainly, if I could find the derivative of V1 and the derivative of V2, that wouldn't be something I would look the other way on. I mean, that would be pretty close to what I want. If I could find just V1 prime and V2 prime, that would be nearly what I want. Then I could just integrate to finish the job. Yeah. So look at what we got. We've got, you know, Y1 V1 prime plus Y2 V2 prime equals to 0. And this one gives me y1 prime v1 prime plus y2 prime v2 prime equal to a, well, excuse me, g over a. We are assuming a is non-zero here, all right? Although a could be a function. A, b, and c in this derivation could equally well be functions. It doesn't change anything we've done, by the way. So look at that. Well, hey, look, this is nothing more than the 2 by 2 matrix equation, y1, y2, y1 prime, y2 prime, times the column vector v1 prime, v2 prime, equal to 0, g over a. Now, if you know about matrix and matrix multiplication and column vectors, great. If you don't, here's an introduction. A poor introduction. We've got 5 minutes, right? So I'm not going to belabor it. We'll come back to this stuff later in the course, yeah. But the larger point here is there's a formula for the 2 by 2 inverse. So I can multiply both the sides of this equation by the inverse to this matrix. If I think about this matrix being A, and think about this being V prime, and think about this being, say, F vector, then linear algebra says that V prime is equal to A inverse times the F vector. But there's a formula for A inverse. If I do A, B, C, D inverse, the inverse is 1 over AD minus BC. You flip the diagonals, and you put minuses on the off diagonals, minus B minus C. So that's the formula for A inverse here. So what I'm trying to say is that V1 prime, V2 prime should be equal to 1 over AD minus BC, which is Y1, Y2 prime minus Y2, Y1 prime. And then I flip the diagonals, Y2 prime, Y1, put minuses on the off diagonal, minus Y2, minus Y1 prime. I'm supposed to multiply that thing times the 0 and g over a. What's that give me? It gives me, well, minus y2 g divided by a times y1, y2 prime minus y2, y1 prime for the first component. And for the second component, it gives me y1g divided by a times y1, y2 prime minus y2, y1 prime. In summary, we have just worked out that dv1 dt is equal to minus y2 g over a, well, times the Wronskian of y1 and y2, yeah? And likewise, dv2 dt is equal to y1g divided by a times the Wronskian of y1 and y2, right? Those are the Wronskians. Like, it's the determinant of the little 2 by 2 matrix, which I have actually, in fact, that coefficient matrix to this 2 by 2 system is the matrix whose determinant is the Wronskian, which is good news because that means that this inverse exists because a fundamental solution set has non-zero Wronskian by Abel's formula. Prove that another day, I remember. I do believe. All right, so after the dust settles, we derive, what are the formulas? V1 is the integral of minus g y2 dt over a y1 y2 prime minus y2 y1 prime, right? And V2 is equal to the integral of g y1 dt over a times y1 y2 prime minus y2 y1 prime. These formulas that I just wrote down, I think they're equation 10 in your textbook. I believe the differential equations that set them up are equations 9. Again, if you look at other instructors, they'll actually make you solve the differential equations 9. But I prefer that you use the integral formulas I just wrote down with understanding, because every time we use those, we're actually going through that whole multiplication by the 2 by 2 inverse matrix. In other words, there's a 2 by 2 system of equations that we've solved when we use this formula. Okay. Anyway, what does this look like for this problem? What's my g? What's my y1? First of all, what's y1, y2 prime? What's y1, y2 prime minus y1, y2, y? Y1, y2 prime minus y1, y2, y1 prime. What's that equal to here? That's cosine squared t plus sine squared t. Well, this problem is very nice because the Wronskian of this cosine sine solution set is 1. And what's a equal to here as well? Ha! Silence! All right, a equals 1 as well, right? So these formulas simplify very nicely. This is g, right? Secant g. So what you're looking at is the integral of minus secant t. What's y2? Sine t, yeah? Secant t sine t dt divided by 1 times 1, right? And this one is the integral of, even easier, secant t cosine t dt over 1, yeah? So let's see here, continuing, what's my v1 equal to? The integral of sine, well, minus sine t dt over cosine t, yeah? And my v2, well, v2 is just the integral of dt, isn't it? Because secant and cosine are, just cancel, right? Secant's 1 over cosine, so cosine times secant is just 1. I'll do the second integral. You guys do the first. U equals cosine, right? This is just natural log the absolute value of cosine t, yeah? Now, you can add a constant here, but you don't need to. It's a lot like the integrating factor method. Why didn't we add a constant when we calculate the integrating factor, by the way? Very well, yeah. I mean, I think it's because if we add a constant to that like the integral of the integral of p dx, it's just basically like multiplying the integrating factor by a non-zero number, because you exponentiate it. So, like if I works as an integrating factor, then 10 times I works, so we don't care. We just don't care. Here, if I add constants, it just adds a copy of the homogeneous solution. So here we go. Therefore, y is equal to, well, yp is v1, which was what? That. And y1 was, so I got cosine t, natural log the absolute value of cosine t. That's my y1 v1. And then plus, looks like t times sine t, that's my v2, my y2 v2. There you go. That is a particular solution. And so, Grace, to be more clear, the instructions for this one was find a particular solution. And that's in the technical sense of particular solution, right? Well, I guess it doesn't need to be technical, non-technical. It's all good. But this is this is called variation of parameters, and this is what we do when the annihilator method and method of undetermined coefficients lets us down. For what g does this derivation I just went through work? There are no strings attached, are there? Because this is just, this is born on the existence and invertibility of the matrix of coefficients over there, which is just to say that the fundamental solution set must be as advertised, a set of linearly independent solutions. And if it is, the Wronskian's non-zero, which means that integral makes sense, provided that we can integrate g, right? So I guess you do need g's like piecewise continuous or something like that. I mean, certainly if g was too ill-behaved, it would be hard to integrate it, right? I've just showed you the derivation for the second order case. This can be extended to order 3 and in fact to order n. It involves similar calculations to the ones I showed you before for the nth order Wronskian. It's quite nasty. So I think, unless there's somebody here interested in it, I think I'm just going to go on to applications next time, and we won't even cover higher order variation parameter if it's okay with you guys. I could do that. No, I mean, if I don't cover it in class, I'm not going to test on it, no. So the answer to my question is yes, please don't cover higher order variation parameters. This is a no-brainer, you guys. I mean, like, yes, we want to see more applications and second order examples, please, please, please. Now, higher order undetermined coefficients are possible. That wouldn't be, that method extends naturally to higher order, but I shut up. See you guys Thursday. Did you hit the stop record, Rifkin?